Section 4.5 is integration by substitution. First, we have to learn the substitution rule for indefinite integrals. Sometimes we can rewrite an integral to a simpler form, and this is the substitution part. We let u equal g of x, then du would be g prime of x dx. Notice this is just differential form. And we do that to get this to happen. If we have a complicated integral, so here we have the integral of f of g of x, so we have a composite function, times g prime of x dx. Now here's the substitution. If we let u equal g of x, then f of g of x becomes f of the u variable. The u variable replaces g of x. Then because du would be g prime of x dx, that means we can replace g prime of x dx with du. And now we have a much simpler integral to do. We know the antiderivative of little f is capital F, and that would still be of the u variable. We have to add a constant of integration because it's an indefinite integral. And then, because the original integral was in terms of the x variable, we have to substitute back to the x variable and replace u with g of x. And remember, we're using that convention where the derivative with respect to x of capital F of x is little f of x. Let's try an example here. We have the integral of the quantity x cubed plus 7 raised to the 5th power times 3x squared dx. Without substitution, we couldn't easily evaluate this integral, but here's the substitution we'll want to do. Remember, whatever the inside function of the composite function is, that's who we want to put equal to our new u variable. So in this case, we're going to let u equal x cubed plus 7. And then we have to figure out who du equals. Du is going to equal the derivative of this, which is 3x squared dx. Remember, we are using differential notation here. So instead of writing du over dx equals 3x squared, we are writing du equals 3x squared dx. Now, let's substitute those in to our original integral. One of my suggestions to you is going to be that you use highlighters. So here we have this quantity x cubed plus 7 to the 5th is going to become u to the 5th. And then this 3x squared dx, we see that we can replace with du. And what you want to make sure that you have is that everything from the original integral has a new face in the u variable. There can't be anything left over. Now that we have u to the 5th du, we know that that would equal u to the 6th over 6 plus c, the constant of integration, because it's an indefinite integral. Now we have to substitute back to the original variable, which was in terms of x. So this becomes 1/6 times the quantity x cubed plus 7 to the 6th power plus c. In this example, we have to integrate sine cubed of x cosine of x dx. It's important to remember that this notation, sine cubed of x, means that we are integrating the quantity sine of x to the 3rd power times the cosine of x dx. Now here we can do what we call a U-du substitution if we let u equal the inside function of the composite function. Notice that this quantity sine of x to the 3rd power is a composite function. The inside function is sine of x, so that's who we will substitute with u. Then du is going to be cosine of x dx, because the derivative of sine is cosine, and we're writing this in differential notation. So instead of du dx equals cosine x, we are saying du equals cosine x dx. Now we are ready to do our substitutions. Bring down the equal sign and the integral symbol. Here in the original integral, we had the quantity sine of x cubed, and we're going to be able to replace that with u cubed in our new integral. Now we will need du here, and it turns out that du is equal to cosine of x dx. So we can replace cosine of x dx in the original integral with du in the new integral. And once again, I really suggest that you use the highlighters, because you have to make sure that every single item from the original integral is replaced in the u variable integral. And here, cosine x dx in the original integral is replaced with du in the new variable. And the reason we can do that replacement is because once we set up the u variable, we found that its derivative in differential notation was du equals cosine x dx. Now this is equal to u to the 4th over 4 plus c, and then we have to switch back to the original variable, which was x. We can write the 1/4 out front. We know this would be sine of x to the 4th power, so we can write it sine to the 4th of x plus c. In this example, we have the integral of 2x times the square root of quantity x squared plus 1 dx. Now, we have a composite function here with the square root of quantity x squared plus 1, so that's a good place to aim for our u variable to be the inside function, which is x squared plus 1. Then that means du would equal 2x dx. And that's a good sign, because we see that we have 2x dx there. Now before we do the substitution, we might want to reorder things a little bit. We've got integral. I'm going to write this radical first, and I'm going to use exponential notation. So I'll write it as x squared plus 1 to the 1/2 power. So we've got that taken care of. Then we have 2x, and we have dx. Now, let's go ahead and do our substitutions. So we have the integral of this first expression right here in the x variable turns into u to the 1/2. So we can highlight that, and that's taken care of. Then this 2x dx we see can be replaced with du in the u variable. And now we've checked everything from the original integral has been replaced in the u integral. And now this is a very simple integral to do. We get u to the 3/2 divided by 3/2 plus a constant. We know that dividing by 3/2 is the same as multiplying by 2/3, and then we can switch the u variable back to the x variable, and this becomes x squared plus 1 to the 3/2 power plus the constant of integration. Here we have to integrate secant squared of x over 5 tangent of x over 5 dx. Whenever you do a UDU substitution, you're always looking for some part of the integral to be the derivative of another part of the integral. So in this case, for example, we could let u equal tangent of x over 5. Then du is going to equal, we know the derivative of tangent of something is going to be secant squared of the something, and then chain rule tells us that we have to take it times the derivative of what's inside, which would be 1/5, and then we're in differential notation, so we put the dx here. So du is equal to 1/5 secant squared of x over 5 dx. Before I do any substituting to the u variable, I first want to reorganize the x variable integral. So we have the integral of, now we're letting the u variable be tangent of x over 5, so I'm actually going to write that first. Tangent of x over 5. We have secant squared of x over 5, and we have dx. But looking ahead, we see that our du is going to require that we have 1/5 secant squared of x over 5 dx. So I'm going to purposely leave some space right here and just move the secant squared of x over 5 and the dx over. Secant squared x over 5 dx. Because right now I'm just moving the items from the original integral over to this new integral. Now, because we know when we do our substitution, we can't replace du unless we have this exact quantity, all of that. What we see that we're missing from the original integral and what we've reorganized over here is the 1/5. So if we put a 1/5 on the inside, we could counteract that by multiplying by 5 on the outside. Because 5 times 1/5 equals 1. So we haven't changed what the integral is. Now we are ready to do our substitution. We bring down the equal sign. We have this 5 out front. That has to come down here. We have the integral of tangent of x over 5 is going to get replaced with the u variable. And then all the rest of this, 1/5 secant squared of x over 5 dx, that whole entire thing gets replaced with du. That's the power of the Udu substitution. It takes a more complicated integral and turns it into something simple. Now when we integrate this, we have 5 times u squared over 2 plus c, which means when we switch back to the x variable, we have 5/2, then replacing the u with tangent of x over 5, we can write that tangent squared of x over 5, because we had u squared here, and then we bring down the plus c. In this example, we have to integrate the square root of quantity 4 minus 3x dx. Now doing our UDU substitution, we want to let the u variable be the inside of the composite function, which is 4 minus 3x. Then du is going to equal negative 3 dx. So here, let's reorganize our integral. We have 4 minus 3x to the 1/2 power. Then we have dx, but we see that we're going to need negative 3 dx. So once again, I will leave some space here and write the dx. We are going to put in that negative 3 that we need and counteract it out front with a negative 1/3. That way, we are really only multiplying by 1, because negative 1/3 times negative 3 is equal to 1. So we haven't changed our original integral. We've just changed the format a little so that we can do this substitution. This is going to equal, we have to bring down every element from the x variable and convert it to the u variable. The negative 1/3 constant out front stays there as negative 1/3. Then we have the integral. The quantity 4 minus 3x to the 1/2 power becomes u to the 1/2. And the negative 3 dx we see can be replaced by du. Now this simplifies to be negative 1/3. We have u to the 3/2 over 3/2, which we know is multiplying by 2/3, plus c. Now we have to simplify and go back to the x variable. So this becomes negative 2/9. We replace the u with 4 minus 3x. So we have quantity 4 minus 3x raised up to the 3/2 power plus c. Now you will learn to evaluate integrals involving a double substitution. In this example, we have the integral of x times the square root of the quantity 2x minus 1 dx. Now if we let u be the inside of this composite function, so that u is equal to 2x minus 1, then du is going to equal 2 dx. We can rewrite this integral as x times the quantity 2x minus 1 to the half. I'm going to leave some space here in front of the dx because I see already that I'm going to need a 2 there. So if we put the 2 there that we need, then we have to counteract that with a 1/2 out front so we don't change what we have, because 1/2 times 2 equals 1. So we're only multiplying by 1. Now let's start doing our substitutions. We know out front here we can bring down that 1/2. We have the integral. We know that this quantity 2x minus 1 to the half is going to be replaced with u to the half. And we know that 2 times dx is going to get replaced with du. And now you're going to see why I really suggest the highlighters. We notice that not everything in the original integral has been replaced yet. We still have this x that needs replacing. So what we can do is take this substitution we did, u equals 2x minus 1, and we can solve it for x. So that means we would need to bring the minus 1 to the left-hand side, so then it would become plus 1 over there. And then we would need to divide by 2, and now we would have the x by itself. Then that means anywhere that I see an x, which is right here, I can replace it with the quantity u plus 1 over 2. And that's what we're talking about when we say we are doing a double substitution. We're having to substitute in two ways here. So this becomes u plus 1 over 2. Now, every element from the original integral in terms of x has been replaced with its corresponding element in the new integral with u. Now let's start to simplify here. This 2 right here is a constant. Let's bring it out front as another 1/2. So 1/2 times 1/2 means we have a coefficient of 1/4 out front. Then that means we are integrating the quantity u plus 1 u to the half du. In this form, we can't integrate that yet, so we write it as 1/4 times the integral, and we need to distribute. U to the 1/2 times u is u to the 3/2 plus u to the 1/2 times 1 is u to the 1/2 du. Now we can integrate this. We have 1/4 times the quantity u to the 5/2 over 5/2, which means I multiply by 2/5, plus u to the 3/2 over 3/2, which means we multiply by 2/3, and then we can just throw the constant of integration over here on the end, plus c. What we are going to want to do is factor this. So we have 1/4 times the quantity. I recommend that you get the common denominator first, and between 3 and 5, that common denominator is 15. So this first term is going to become 6 u to the 5/2 plus the second term will become 10 u to the 3/2 plus a constant. We continue to simplify. 4 times 15 is 60, so we have 1/60 out front. And we see from this numerator here, we can factor out a 2, and we can factor out a u to the 3/2, and we would have left 3u plus 5. And we still have the plus c over there. So always double check your factoring. 2u to the 3/2 times 3u is going to give us 6u to the 5/2, and 2u to the 3/2 times 5 is going to give us 10u to the 3/2. This is going to equal, we can cancel a 2 from the 60, and now we have 1 over 30, and the u to the 3/2 can get replaced with 2x minus 1 to the 3/2. On the inside, we have 3 times u, and we're going to replace that u with 2x minus 1. Then we have plus 5, and then our constant of integration plus c. So this is equal to 1 over 30 times 2x minus 1 to the 3/2. And now we have 6x, and we see we would have minus 3 and then plus 5, so that's plus 2 plus a constant. Now from here we can factor out a 2, so we are still simplifying. Bring down the 1 over 30, 2x minus 1 to the 3/2. Then we will multiply that times 2 times the quantity 3x plus 1 plus c. Now this 2 will cancel with the 30 in the denominator here. So finally we get 1 over 15, 2x minus 1 to the 3/2 times 3x plus 1 plus c. And this is in simplest factored form. In this example, we have to integrate x to the third power times the cube root of the quantity x squared plus 2 dx. Now, if we let our u variable be the inside of this composite function, x squared plus 2, then du is going to equal 2x dx. We are going to need to do some reorganizing of our x integral here. So we have the integral. Now, from this x cubed, we see that we could take an x and move it over here by the dx because we're going to need that. You can think of x cubed as x squared times x, and I'm going to take this guy, move it over by the dx because I'm looking ahead to see that I need that as part of du. So then this x squared that's left over, let's just write that here. Then we will have x squared plus 2 raised up to the 1/3 power. Then I'm going to leave a little space here, take this x, put it next to the dx. And of course, the reason I left this little space here was because I see that I need 2x dx. I don't have it. There's no 2 in here. So if we put in a 2 here, we have to counteract it with a 1/2 out front. So now all we've done is reorganize this original integral in terms of x, move things around. So we have an x squared here times an x, which takes the place of this x cubed in the original integral. We have the cube root of x squared plus 2, which is here, and we have the dx, which is here. Now we've inserted 1 in the form of 1/2 times 2. Now we can begin to replace into the new u integral. This 1/2 out front is going to come straight down, stays 1/2. We have the integral symbol. We see that we have this x squared here that we are going to have to substitute for, and this will be the double substitution we have to do because we have to take this and solve for x squared. So all we need to do is move the plus 2 over to the left hand side as a minus 2, and we get u minus 2 is equal to x squared, which means anywhere that we see x squared, we can replace it with u minus 2. So this x squared right here becomes u minus 2. Then we have the quantity x squared plus 2 to the 1/3 power that we are going to replace. And in the u variable, that will become u to the 1/3. And then finally, we have 2x dx, which is going to get replaced with du. Let's simplify. We have that 1/2 out front, integral. We can't integrate when we have a quantity times a quantity inside the integral. We have to distribute that u to the 1/3, and we would get u to the 4/3 minus 2u to the 1/3 du. Now we can integrate, and we have 1/2 times the quantity u to the 7/3 over 7/3, which means we multiply by 3/7, because adding 1 to 4/3 means we're adding 3/3. 4/3 plus 3/3 gives us 7/3, minus, we bring down this 2, and then u to the 1/3 is going to integrate to become u to the 4/3 over 4/3, which means we multiply by 3/4, and then we can add the constant of integration at the end. So now we have 1/2 times the quantity 3u to the 7/3 over 7 minus 3u to the 4/3 over 2, because the 2 goes into the 4 twice, plus c. We continue to simplify, bring down the equal sign and the 1/2. Let's get a common denominator on the inside of the brackets here. Our common denominator would be 14. So this first term becomes 6u to the 7/3 minus the second term, which would become 21u to the 4/3 plus c. Now out front here, we can combine the 2 and the 14 in the denominator, and we now have 1 over 28. And we can factor this numerator, taking out 3u to the 4/3. We would need to multiply by the quantity 2u minus 7, and then add our constant of integration. Now double check your factoring. 3u to the 4/3 times 2u is equal to 6u to the 7/3, and 3u to the 4/3 times a negative 7 gives us negative 21u to the 4/3. So now we have 3 over 28, and let's substitute back to the x variable. Remember that u is equal to x squared plus 2, so u to the 4/3 becomes x squared plus 2 to the 4/3. Inside the bracket, we have 2 times the quantity x squared plus 2, and then we have to subtract 7, close the bracket, add c. Simplifying, we get 3 over 28 times x squared plus 2 to the 4/3 power times the quantity 2x squared. Then we would get plus 4 and minus 7, so that's a minus 3, plus c. And thankfully, nothing else factors, so we're finally finished here.